How do objects move? So that's going to be the question today. It may seem like an overwhelming and daunting task to cover in just one video, but secretly, I've been preparing you for this exact topic. Oh, diabolical, I know. But if you haven't watched my previous videos, feel free to check them out. They should bring you up to speed. But for today's video, we're going to study how objects move by looking at how they fall, and inevitably have a great exercise on how to use physics and data and models to understand things. Just remember, you got this. Okay, let's get into it. Howdy everyone, I'm Biscuit. And to figure out how objects fall, we're first going to need a ruler, a camera, and an unwilling test subject. Here's my friend Mr. Duck, who's going to fall and wait, what's that? You want a parachute? Sorry buddy, the budget doesn't allow for that, Wait, what? Unsafe working conditions. Workers' rights. Okay, I'll give him a pillow. Okay, let's go over the theoretical basics of motion, which are Newton's laws of motion. What we're concerned about today is the first law of motion. We'll cover the other two in later videos, as they're just whole topics in and of themselves. But the first law of motion states that objects in motion tend to stay in motion, while objects at rest tend to stay at rest. So what that means, if I leave my little buddy here on the table, he's just going to sit here and stay motionless unless something interacts with him and interferes with him being motionless. But contrary, if I give him a little push, he should just continue moving on forever and ever and indefinitely. Oh, okay, what just happened? He didn't move on forever. Well, it turns out after I pushed him, something pushed back, and we call that friction. And we can feel friction by rubbing our hands together. Those small little imperfections in our hands and the surfaces tend to take that energy of motion away and convert it to thermal energy. In other words, heat. So we live in a world where friction is really common. So it can be difficult to see the first law of motion working in everyday life, apart, from just laying around and being a couch potato. Fortunately, there's some places with almost no friction, such as outer space. There, if you throw something away from you, it'll just keep moving unhindered until maybe forever. That is the true nature of motion in the first law. So now we're going to do a little test and let this guy fall, and we're going to find that our friend doesn't really move unhindered when we let him go. To track how he's moving after he falls, we're going to use a tape measure and see how high he is at a number of points in time. Now normally my camera records at 30 frames per second, but we're going to increase that to 120 frames per second, and then record his height every 30 frames, which is every 1/4 seconds. Okay, it's just about time to let him fall, send him on his way. Godspeed, Mr. Duck. Type 7 in the chat for Mr. Duck. Okay, as Mr. Duck falls, we're going to plot his height as a function of time. So the x-axis on this graph on the right, it's going to be time in seconds. The y-axis is going to be his height in terms of inches, and it was inches because that's all I could read on the ruler. And I have a number of error bars that are going to be there. I put about an inch because that's about what I could distinguish his height at. Okay, so let's just let him fall to see what happens. Okay, in the end we get this curve shape, which we call a parabola. We see that he starts out slow, but then picks up more and more speed over time until he finally hits the ground, or pillow. Well, why did we get this result? Well, we can understand it by building a model motivated by what's happening to the duck as he's falling. So why did the duck fall? Well, it's because he was accelerating due to gravity. Okay, gravity is just the force of all the different masses attracting each other from a distance. This means every object on Earth was simultaneously pulling on him, and this combined pull can be summed up to a single number, an acceleration of 9.8 meters per second squared, often written as a small g. Our goal is going to be to write down an expression that tells us his height given a time. Now what's going to follow is a decent amount of math, so don't worry too much about it if you don't have a math background, but just focus on the reasoning behind it. Since acceleration is the time derivative of velocity, we can write this mathematically as this. Now our goal is to first solve for the velocity here, which just means we just want to get v equals a bunch of stuff. To do that, we need to solve this differential equation, where a differential equation is just an equation with a derivative in it. Now solving differential equations is an entire field of math unto itself. But here we're going to use the simplest method, integration. But again, don't worry too much about the specific math if you don't have the background. Just know we're deriving an equation to serve as our model using a few simple assumptions. So we get the equation v equals v naught plus at. So that's saying if given any time t and an initial velocity v naught, we're able to tell you what the velocity is of this kind of object at any given time t. Now, what we actually want is an equation for height, but we currently have velocity. So recall velocity is the time derivative of displacement. And so we're gonna have to integrate again and yada yada. We go and do that, we get this equation. So now we have height as a function of time, meaning after we specify a couple constants, the initial height and initial velocity, we can put in any time and now get back the correct height. So in this scenario, Mr. Duck started 36 inches off the ground, or about 0.915 meters. So we're gonna put that in for x naught. Secondly, we dropped him from rest, so the initial velocity should be 0. So let's set that. Thirdly, we're accelerating downward at 9.8 meters per second squared. So since this is pointing down, we're going to choose positive being up. We're going to put a negative sign here. Okay, that's going to leave us with this equation. If we plot this along our data points, we're going to find that it fits okay. It turns out, so I'm recording this after I did the rest of the video. I didn't realize that actually our data was going to fall a little bit off of this basic model, which we called kinematics. So it turns out air drag is the reason this is going to happen. So when I talk about air drag later, just know that I sort of underestimated the effect it was going to have. Now we can do the same experiment by throwing a little buddy up here, straight up in the air. Now if everything goes well and, you know, he survives, we can expect the same model to match this scenario. We just need to change the starting height and add an initial velocity. Okay, so we throw the duck up, we go and plot the points of his height next alongside him, just like we did with when he was falling. Okay, and then if we compare that to the model we have for an object falling at a constant acceleration, we find that it fits even worse than before. So we're finding the air drag is becoming a really big problem here because the duck's in the air a lot longer, and this means the effect has more time to accumulate and really affect our results. So again, let's keep this in the back of our mind. Usually kinematics is an okay assumption, but we're gonna go back and address this in the end of the video. Okay, we solved the problem of all objects falling. I mean, we might as well take a victory lap and do another object. So I got a piece of paper here. You know, if we drop it, you know, we'll just find it falls at 9.8 meters per second squared. And oh, that didn't fall like before. That didn't fall like the duck. What happened? So it turns out our assumptions based on it compared to the duck were wrong. Since paper falling face down has such a large surface area, it experiences a large amount of air drag, air pushing up and resisting its movement. And since it weighs so much less, this force matters way more. To account for this, we need to add an additional term to our original differential equation. It looks like b times v squared. B is some just coefficient. And the resistance goes as v squared instead of just v, because it's a large object. Turns out small dust-like sized particles experience air drag just as v, but compared to large objects. Okay, so let's just put this in a differential equation. We'll solve it in a computer this time. You know, don't worry about math by hand. And you know, we get, oh, ooh, well, that looks disgusting. Well, even so, if we pick the right constants, we should get something that matches our data. Now I'm going to use a coffee filter instead of a piece of paper, so it tends not to sway as it falls, but you can see how this additional term changes the answer by a bit and better fits the coffee filter's data falling, just including this term. Now you may object to not using the term in the first place. You know, when we drop the little rubber duck, I mean, well, as he's falling, he is experiencing air resistance and drag. But to that I say, when we're doing science, we need to hold to the principle of Occam's razor, which states, do the simplest thing first, dummy. Often the corrections are just too small to really make a difference. Again, in physics and engineering, we need some sort of tolerance to decide what we're comfortable with. Often it's not better to spend 100 times the effort just to get 1% better in the end. You need to be pragmatic in science. Otherwise, you'll spend the rest of your life solving a simple problem while the rest of us are outside drinking cocktails. Okay, so we're able to do an experiment with how Mr. Duck fell and accurately modeled his motion using a few basic assumptions. And that's how science works. We need to match models with data. Sometimes the data comes first and we need to make a model to fit it. And sometimes we make models and verify them using experiments. Regardless, I hope you learned something. Also, I really appreciate all the support lately on the channel. I know a few people have been sharing around the videos, but just thank you everyone. If you like this, let me know, or if you have any other ideas for videos, let me know in the comments below, or just if you have anything else to tell me. Okay, thanks for watching. Okay, bye. And that's how science works. We need to match, oh my God, I need to eat.